by, like 2 times more massive, 2.5. The average lifespan of a muon is 2.25 microseconds. Oh, another use of mu. 2.25 microseconds, so 2.25 times 10 to the negative 6 seconds. This is the average lifespan. They clocked the speed of these at 0.989 times the speed of light. And generally in physics, unless you are 10% of the speed of light or faster, you ignore relativistic effects. This is definitely 10% or faster. And that comes out to, well, speed of light is about 3 times 10 to the 8th. Do the math. And so it comes out to about 2.97 times 10 to the 8th meters per second. The difference in height, let's just go ahead and do 1219 meters. All right, so what we need to figure out is if special relativity doesn't exist, how many lifetimes will pass by the time it gets to here? Or how many half-lives will happen? Well, if I have some sort of decay going on, there is a generic formula for that, that the number of particles should equal some initial number of particles times e to the negative t over tau. That's for average lifespan. There's another one that you might run into if they were dealing with half-lives. If we're dealing with half-lives, there's the n equals n sub naught times 1/2 to the negative t over the half-life. But we're using the top one. All right, so in reality, wow, my notes suck. So nothing I've written up here is wrong, but what I did mistakenly say is actually my calculations on my paper here, I'm using the half-life. So I need to tell you what the half-life is. Oh, sorry, and one correction, that's the wrong one. That minus sign doesn't need to be here. If it's a 2, then I need the negative there. If it's 1/2, I don't put the negative in. I apologize for that also. The half-life of a muon, 1.56 microseconds. So after every 1.5, roughly 1.5 microseconds, I've lost half the muons should just disintegrate. All right, so let's figure out how much time, because I know that it's, I'm thin here. I've measured these heights. I know the difference here. So if it's traveling at that speed for that distance, how much time passes? get?
I might have done it wrong. 4.369 times 10 to the negative 6.
Yeah, you used this number down here?
No.
Oh, no, sorry, not that number. Use this number and that number. Okay, yeah. Apparently I was using some totally different numbers. So you get
4.369.
4.369 times 10 to the negative 6
Yeah.
seconds. Okay.
Is that right?
I had 4.11,
Okay.
so we're close enough.
Okay.
So that's the amount of time that passes. So if I plug into my formula here, I would expect that the number of particles will be, well, what I start with. I start out with 550 muons per hour times 1/2 raised to the amount of time, this number right here, divided by 1.56. I am going to change that slightly. I'm going to change the way I write it. 4.37 microseconds and over 1.56 microseconds. Just so we don't have to worry about the times 10 to the 6th, since they both are times 10 to the 6th. So first off, if you could tell me what that fraction is before we get the final answer. So just this part. Just probably 2.8. The units will cancel.
Oh, got it,
So it's 2.8. So almost 3 half-lives. So I would expect after 1 half-life, half of them are gone. I should be down to 275. Another half-life goes by. Then cut that in half, so 137. Cut that in half for 3 half-lives. We definitely have a noticeable shift. So what is the number that we would expect? Or 79. We aren't expecting a fractional bit.
You're right.
So we would expect 79 muons per hour in Echo Lake. Now, that's from our point of view. Our point of view, it goes 1219, it's going 2.97 times 10 to the 8th meters per second. Sorry, 1219 meters at near the speed of light. We do the basic math, calculate how much time that should take, and how many lifetimes from what we know. Now let's assume special relativity has merit. From the muon's point of view, in the proper time, well, first let's figure out what gamma is. This is the Lorentz factor. Lorentz factor. And it is 1 over the square root of 1 minus v squared over c squared, which in our case is 1 over the square root of 1 minus 0.989 squared. The Lorentz factor will keep popping up throughout relativity. So there are many times where you just calculate what that number is, and then you just think through, all right, which of these two numbers should be bigger? And then multiply or divide accordingly. What is this? Still too far.
Second.
No units.
Yeah, this, you have, speed has units, but I have speed divided by speed, the units are gonna cancel out there. All right, so we have this factor here of 6.76. So we have these two frames here. We have the muon's point of view, and then we have our point of view. If we're timing how long it takes the muon to travel, that definitely is not the proper frame, because we are timing how long it takes for something else that is moving. So from the muon's point of view, they are in the proper frame.